So our speaker is Professor Neal Weiner from New York University. He is there in the Center for Cosmology and Particle Physics. And that's no coincidence. He actually is an expert on both the fields of cosmology and particle physics. Particle physics is the study of what happens at the very, very smallest distances, what everything is made of at the smallest distance inside the atom, inside the nucleus. That's what particle physics is, and of course cosmology is exactly the opposite, the study of the largest structures, the study of the universe as a whole, the evolution of the universe as a whole, and the ingredients in the universe. And since the ingredients inside the universe are, well, us, and we're made of particles, so the ingredients include particles, these two fields are actually intricately connected. And in particular, dark matter is a thing that we're studying both in particle physics and in cosmology. And Professor Neal Weiner is an expert on dark matter, and he'll tell us a story about dark matter today. And the one thing I forgot to tell you is he also got his PhD from Berkeley in the year 2000. And then he did a postdoc and got his faculty position at NYU. And there he won multiple awards. He is a Simons Fellow, for example. He's a Catley Fellow. And he won an NSF Career Fellowship for junior faculty. So he is really one of the world's experts on the field and in the field of dark matter. And the field has recognized him. But let's hear from him. Microphone on? Microphone on? No? Is it on now? Yes. Good. So, thank you all for coming out. I want to thank the Center for giving me this opportunity to talk. I'm going to talk today about a topic that's near and dear to my heart and has dominated a lot of my research and a lot of people's research over the last decade. I want to tell you the story, or a part of the story of the dark universe. It's like the force. It's all around us. It holds the galaxy together, and how we're going to find out about it. So let me back up before I get into actually talking about dark matter and talk a little bit generally about scientific principles. So historically, there have been a couple of different ideas that have been incredibly successful as general scientific motivators. One of them is something I can call atomism, the idea that the things that we see are made out of smaller and simpler objects. So stuff is made out of atoms, atoms are made out of protons and electrons, and so forth. And the other idea is something that I'll refer to as Copernicanism. Copernicanism is the idea that we are somehow fundamentally not special. And that idea has actually played a huge role in how we think about physics and cosmology. So you can think about the evolution of the Copernican idea, where we began with the Earth as the center of everything, and we gradually had to relax that idea to being not the center, but pretty close to it. And then we found that that actually wasn't even close to the center. The center was over here. We were just sort of here in the suburbs. And then we found that actually our galaxy wasn't even a particularly unique one. It was just one of many, many, many galaxies in the universe. So we've come from thinking that we are in some incredibly special place to realizing that we are somehow not special. We are in a very generic place in the universe. And that's changed the way that we think about particle physics and cosmology. And what's going on now is we're taking the next step. We've come to take the next step, which is that not only are we not in a special place, we're not only not the important stuff in location in the universe, we're not even the most important stuff in terms of stuff in the universe. We've come to realize, and I'll go into this bit, that most of the energy in the universe is something that we do not know what it is. So if you were to take a gigantic box, millions of light years across, and you were to add up all the energy into it and ask of what form does it take, you would find that almost all of it, 73% of it, is some weird energy associated with the space itself. Then there's some matter in it that can actually cluster and clump into smaller objects. That's dark matter. And the only thing that we know about dark matter is really that it is not us. So there's this tiny sliver of stuff, which is protons, neutrons, electrons, atoms, all that stuff clumped together is 4%. And then, of course, of that, a tiny fraction, 0.4%, is then collapsed into the objects that we live by, like the sun, and that provide the energy for all So we've gone from thinking that we're incredibly special in all respects to not even thinking that we're special in terms of the stuff we're made out of. We're out on the fringe here in terms of material. So if the universe is made out of all this dark stuff, as a scientist, the natural question you want to ask is, what is it? What's it made out of? How does it behave? And we find ourselves a bit in the situation of Dennis here, who comments, lots of things are invisible, but we don't know how many because we can't see them. And this is true. This is the fundamental problem that you confront as a dark matter physicist, which is you want to understand what that stuff is, but you can't see it, so then how do you look for it? That's the basic problem that we confront every day. So, the dark universe. These are the questions. What's out there that we can't see? What might it be, and how do we find out? These are the questions that we confront. Now, I want to start by telling you one thing about the ending, which is that I don't know what the ending of this story is. We are in the middle of this story, and I can't tell you what dark matter is, because I don't know. And I can only tell you about how we're trying to find out what dark matter is. But what I can tell you is that a big question that we're going through right now is the question of, is this going to be a search of lampposts, or is this going to be a search of elephants? And if you take away one thing from this talk, that's the question that you should remember. Lampposts or elephants? Okay? Good, you can go. So, a brief outline, and I'll describe what I mean. Where will we go in this talk? I'm going to start by describing the one part of the dark universe that we do know, and how we came to know it, and how we now use it to find out about the rest of the universe. Those are neutrinos. How it forced us to open our eyes to the idea that there's stuff that is not things that we can see. But then from there, we'll move to the discovery of dark matter, the rest of the dark matter, that 23% of the stuff that fills the universe. And then I'll move on to this idea of finding a lamppost. How we might find some way to look for the dark matter, and the approaches people are taking with it. And lastly, I'll discuss the idea of elephants, which are coming with the new satellite called Gaia. So let's begin with the innocent birth of the dark universe. It started a long time ago with a particle that we all have in our bodies, the neutron. It turns out if you have a free neutron, or a neutron in various types of nuclei, it's unstable. So if you just let it sit there, it's going to fall apart. What does it fall apart into? It falls apart into an electron and a proton. And this has been known for a century or more. So what they did when they discovered beta decay, they said, let's go and let's measure the energy of this electron. So here's a paper from 1935. That's a very nice plot of the energy of the electron coming out versus the number. And you see there's this broad distribution of energies that the electron has with some peak. Nothing dramatic about this. But there was something dramatic about this, and it came from the fact that we know that E equals mc squared. Right? More properly, mass is a form of energy, and then energy can be deposited into other forms of energy. So the neutron has some initial mass, and then when it decays, all that energy should be taken away by the electron and the proton. So the energy of the neutron should be equal to the energy of the proton in its mass, and the energy of the electron, which is both in the form of its mass as well as its motion. Okay? So that's the energy that you observe. You see a proton which has some mass, you see an electron which has some mass, the electron also has kinetic energy, and you add them up. But that's the thing. If the neutron has a very specific amount of energy, and these are the things that come out of it, the electron should have a very specific amount of energy, not this broad distribution of energy. Most of the time, when you look at this plot, unless you're way, way out here, down here you find that E does not equal mc squared, that the initial energy you started with does not equal the energy that you ended up with. So that was the conundrum they faced. They knew how much energy they started with, they measured how much energy they ended up with, and they did not equal each other. So along came Pauli in 1930, who said this, a sentiment which is not reflected by particle physicists today. He said, I've done a terrible thing. I've postulated a particle which cannot be detected. Particle physicists have gotten over that. We're now totally fine postulated particles that cannot be detected, but he thought it was a bad thing. What he did is he said, well, maybe there's some other particle, a neutrino, which he called little neutral one, that was carrying off this missing energy. So he was sort of by fiat just saying, well, I'm going to believe that energy is conserved, so this neutrino must be carrying away the energy. I believe the laws of physics that have been established time and time again in all of my experiments. Therefore, if I insist on that, there must be something I cannot see. But from his perspective, it was invisible. It carried no electric charge. It carried no nuclear interactions. It was this massless, wisp-like particle that just vanished from the experiment. And he considered that a tragedy. But it did solve the problem. But he was wrong. It was not invisible. And so let me take you through an approach that many physicists take in how we develop this idea of lampposts. How you start with an idea of what its particle's properties are, and you turn that into a way to look for that particle. So this is the picture that you start with. A neutron decays into an electron, proton, neutrino. If that can happen, then the reverse process should happen. You take an electron, a proton, neutrino, and you turn it into a neutron. Well, if that process can happen, and this is the one little reach I'm going to do, maybe I could move the electron from one side of the diagram to the other side of the diagram by turning it from an electron into an anti-electron. And then this process should happen, where a neutrino comes in with a proton, and it spits out a neutron and an anti-electron. Okay? So you've taken the feature that you use to define the particle, and you turn it into a process that maybe you can use to look for this neutrino. So if this happens, this should happen, and you can look for this. So Rines and Cohen decided to do this. They set up an experiment where they took a nuclear reactor. Nuclear reactors are copious source producers of neutrinos. They put a water tank with some detectors to look for the neutrons and positrons. And they put a wall, a shield, so that the only things that could get through would be the neutrinos. They let it bombard. They looked for the neutrinos producing anti-electrons here. They detected them. That gave, and you could study the rate changing with the energy production of the nuclear reactor, so you had a lot of control of the experiment. And this allowed them to conclusively say, yes, indeed, we have seen the neutrino. So this particle that 20 years previously had been speculated to be invisible was then found. This is their paper, 1953, and they got a Nobel Prize for this. Well, okay, now we can see neutrinos. So are there other sources you can look for? And the answer is yes. The universe is full of radioactive processes. We're bombarded by cosmic rays, which produce neutrinos all around us. And the sun, which of course is powered by nuclear reactions, is the biggest local source of neutrinos that you're going to find, and it's bombarding us with neutrinos constantly. One of the numbers that I'd like to just keep in the back of my head to give you a sense of how important and how big the flux of neutrinos is if you hold up your pinky fingernail, you hold up your pinky, and you look at your pinky fingernail, every second, 100 billion neutrinos are passing through it. Every second. Right? So that's just your pinky fingernail. This entire room is being flooded by hundreds of trillions of neutrinos every second that pass through us and we don't notice at all. That then prompted people to look for those neutrinos. John Bacall here predicted the flux, this number, 100 billion per square centimeter per second, of neutrinos on Earth. And then Ray Davis went underground into a mine in South Dakota, where he built an experiment that more or less looked for a conversion of chlorine atoms into argon atoms, something like a cleaning solution with chlorine in it. The neutrinos would come in, convert one of the protons, convert that atom into an argon atom, and then you would pull out individual argon atoms, more or less, counting individual argon atoms. And Ray Davis saw almost the right flux that was predicted, about a fourth of it. There was a long brouhaha, but it ended up that this experiment was indeed right. This guy was also right. Some of the neutrinos are missing, but that's a whole other talk. But the point was, this was the first step in taking a neutrino from a particle that was invisible to one that was hard to see, to one that was actually being able to use to study the interior of the sun. Now, we have enormous experiments. This is Super Kamiokande. That is a boat. Those are two scientists who are servicing these circles, which are called photomultiplier tubes. This is in Japan. You fill this with water. Neutrinos come in, hit an atom of water in this tank, produce a light signal that is observed here. That allows you to detect the neutrinos. And this is one of the most remarkable pictures that came out of it, which is what the sun looks like in neutrinos at night. So at night, you can take your neutrino detector, observe the flux of neutrinos that have traversed the entire Earth, and make a picture of it. And this is what it looks like. This is a remarkable feat to think about this, right? In less than a century, we've gone from an invisible particle to something that is allowing us to actually directly see the products coming out of the center of the sun. The reason we know how the sun burns and what the processes are that are producing its energy is because we can see the neutrinos in experiments like superconductivity. It's an incredible achievement. So this is how we went from hypothesis, the idea that there must be something there, to a lamppost, speculating on some of ideas of its properties, turning that into a detectable signal, which can be discovered, and then to astronomy, where you actually are using this. So one takeaway is that's an amazing story on its own, how well we've come to use neutrinos, and we use them all the time now for all sorts of things, and they have still mysteries to show us. But the other thing that's important is to know that the dark universe exists. There are particles out there that you cannot see, that are all around you, that are in this room and are in space, that you cannot detect and contribute to its properties. The energy of neutrinos, even though in the universe it's not that significant now, was a very significant contributor to its properties in the early universe. So the question is, are there other things out there that we cannot see? Well, how do you see things if you can't see them? One answer is that you can see their gravitational effects. This is a movie showing the motions of stars in the very, 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 very center of the Milky Way galaxy. So let me just wind up so you can see this again. This here is the year, the clock that's running here. What you see is there are stars that come and loop past something that's right there, but there's nothing that's luminous here. There's nothing producing any light there, but you can see these stars making a loop around it, coming past it, being slung out, as though there's something that is clearly taking them and tossing them aside. And you look at that, and it's very clear. Anybody in this room would look at that and say, there must be something here that is pulling on those, and you would be right. That is the supermassive black hole that lives in the center of the Milky Way galaxy. To our knowledge, all galaxies have large black holes in their centers. Ours is actually not that large by galactic standards. It has a mass of about 1 million times that of our sun. Okay? So it's an enormous, in terms of its mass, and it has this profound effect on the stars around it, but it's, by galactic standards, not that big. But this is the critical question, right? If you can't see something with your eyes, how do you first see it? And the answer is, you see its gravitational effects. There's stuff out there, it should exert a gravitational force on it. So, Fritz Zwicky was the first person to take this idea and use it as a means to look for dark matter. He wasn't trying to discover dark matter, but this was what he effectively did. He looked at the Coma cluster. So the Coma cluster is actually a cluster of galaxies. Okay? So each one of these is a galaxy. Well, some of these are foreground stars, but these are galaxies. And the idea is that they're gravitationally bound to each other. So just like we're gravitationally bound inside the Milky Way, the galaxies in the Coma cluster are gravitationally bound to each other, and they move around in orbits around the center of mass in the Coma cluster. So what he said was this. Look, you go into the galaxy cluster, and you measure the various motions of all these galaxies. Okay? If they're moving slowly, then the gravity is weak. That means there's not much matter. Okay? There's only a little bit of stuff that's pulling on these things. On the other hand, if they're moving fast, then there must be strong gravity. They're being pulled quite hard, so there must be a lot of mass there to pull on them. The more mass, the more gravity. The more gravity, the faster these things move. So he looked at the Coma cluster. In 1933, coincidentally, he said that only about 1% of the mass of the Coma cluster could be visible in the form of stars. Now, that's a long way from where we are now. You don't know that that invisible matter is something exotic. He's just saying, if you look at this galaxy cluster, almost all of that mass is in the form of something that you can't see. Fast forward to 1970, Vera Rubin, as well as others, but most famously Vera Rubin, decided to look at spiral galaxies. So she did something similar. She said, look, you look at a galaxy like this, almost all the stars are in the center of the galaxy. So most of the mass is in the center of the galaxy. As you move out, it gets more diffuse. So as a consequence, near the center, the gravity is strong. You're close to the mass, it's pulling very strongly on you. You should be moving relatively rapidly. But as you move out, you're far away from all this mass. And so out here, there's weaker gravity and you should be moving more slowly. So she studied these spiral galaxies, and that is not what she found at all. This is the velocity versus the radius, and these are the data. And indeed, the velocity increased, but then just flattened out, whereas she expected it to fall off. So if you act like Pauli, and you say, I believe gravity, we've tested it in a lot of environments, then the only conclusion is there must be mass out here that is pulling on those stars to continue them to move very rapidly. And this was a big change, because unlike in Zwicky's case, where the mass could be anything, here the mass is actually behaving very differently. Ordinary matter is clustering in the center. This mass must be out here surrounding the galaxy as well. By now, we have a tremendous amount of information about dark matter. Something that a lot of people will say is, isn't it a big logical leap to say that you see things acting funny and you're going to insert that there's some sort of additional matter there that you can't see? My first answer to that is, no, that's actually the conservative assumption. We know there are invisible particles. It should not surprise us if there's stuff we can't see. This is a very, very reasonable thing to do. But the second thing I would say is, every place we look, we see the consequences of dark matter time and time again. So we look at a galaxy cluster. This is the bullet cluster, which is another cluster of galaxies. And by looking at how light gets bent around it, you can infer where the mass is. And you see this bluish region is where the mass is. But there's also hot ray gas emission, and that tells you where the ordinary matter is. The ordinary matter is where the pink stuff is. So this system is actually a system where two galaxy clusters came and the ordinary matter collided together and slowed down, but the dark matter just continued to move on unimpeded. So these blue regions of dark matter have separated, the pink ordinary matter has slowed down, and we see the presence of dark matter there. But we also see dark matter and its signs in the cosmic microwave background radiation. You look at the light left over from the Big Bang, we see these tiny little ripples in temperature in it, and we can actually predict them. It's technically difficult, but it's not intellectually complicated at this point. It's ordinary physics that we can understand to calculate this. And if you want to understand this fluctuation, you need to have dark matter in the story. It cannot be ordinary matter. We can measure the leftover elements from the Big Bang. So that's lithium, deuterium, and types of hydrogen, and compare them to the amounts that you would expect. And the answer is that you can only explain the amount of these atoms that you see if matter is 4% of the energy density of the universe. If it were more, you would get completely wrong answers for this. And you can look at the structure of the universe. How many galaxy clusters are there? How big are they? How many small galaxies are there? Study that statistically. When you do that, that also tells you that you should have dark matter. The reason why this is interesting and important is that this happens very early in the universe. This is from very early in the universe. And this is from late in the universe. You're talking about things at early times, at late times, at big scales, at small scales, at medium scales. Everywhere we look, we see the imprint of dark matter. So not only is it a conservative assumption to think that it's there, it's passing essentially every test we throw at it with some subtle details that we can discuss later. But how do you find it? How do you find what this is? And the answer is, honestly, you guess. I don't want to sugarcoat it. You try to be smart about it, but you do have to guess. And this is the idea of lampposts. If you think about an electron, how do you look for an electron? You can look for an electron because you know what it is. It has electric charge, it has mass, if it goes through a wire, it can heat it up, it can produce a magnetic field. It has these properties that you know that you can look for. So if you don't know what the properties of the electron are, you have no idea if a magnetic field is telling you there's a particle there or not, or if you see heat, if that's telling you there's a particle there or not. You don't know something about the particle, you don't know what you should be doing to look for. You don't know if you should do the Rhines-and-Cohen experiment to look for the production of anti-electrons. So what you do for dark matter, what particle physicists do, is they start with an assumption about what that dark matter is. Now, if you make a very, very specific assumption, then that's probably not going to work out for you because you have to guess very, very correctly that specific model to be right to find it. But if you go too general, then you're not going to have any interesting signals to look for. So what people do is they try to make the most general types of assumptions they can make and then follow those to their logical conclusions, and hopefully there are some interesting signatures to look for. So let's begin with another picture. The idea that I'm about to describe is something called thermal dark matter. The idea of thermal dark matter is that in the early universe, dark matter and ordinary matter were converting back and forth continuously between themselves. So imagine you have this picture. You start with two dark matter particles. They can come together, collide, and produce say, a proton and an antiproton, an electron and an anti-electron, something like that. The details we're not going to go into right now, but the general idea is there's some process that allows dark matter to come together and produce ordinary matter. Well, if that's true, then our rules of field theory and physics tell us the reverse process should happen. Protons and antiprotons should be able to turn into dark matter. Electrons and anti-electrons should be able to turn into dark matter. So, if that's true, in the early universe, this process, when the universe is very dense and very hot, this process should be going on all the time. Ordinary matter converting into dark matter converting into ordinary matter, continuously, until you have roughly equal amounts of both. But, as the universe cools down, what's going to happen, as the universe cools down, it becomes harder and harder for the ordinary matter to produce the dark matter. Why is that? Well, let's imagine that the dark matter is heavier than the proton. Okay? Then, and a dark matter and an anti-dark matter come together, they have more mass than the proton, so they can make protons and antiprotons. But the proton and antiproton don't have enough energy to produce the dark matter, right? Only really, really energetic protons and antiprotons can produce dark matter. So when the universe cools down, dark matter can still turn into protons and antiprotons, but protons and antiprotons cannot do the reverse process. This means that the universe begins flowing energy density from dark matter into ordinary matter until the universe is expanded so much that dark matter stops finding another dark matter particle to run into, and then it just really floats through the universe forever. So, to repeat, dark matter and ordinary matter convert back and forth. The universe cools down. So, dark matter continues to convert to ordinary matter, but not the reverse process. Eventually, the universe is so dilute that this process stops, and that's the dark matter you're left with. This is the idea of thermal dark matter. There was something that was going back and forth between the two sectors. The protons and antiprotons then go on to annihilate themselves into photons and electrons and things like that. So these things get depleted too. So there's a calculation you can do. And when you go out, you measure the dark matter, you go out and you do these rotation curve measurements, you do your cosmology experiments, you measure how much dark matter is in the universe, and that tells you one quantitative fact. And the quantitative fact it tells you is how efficiently this process happens. If this process were inefficient, if dark matter did not convert into ordinary matter, then there would be lots of dark matter left over. If this process were too efficient, dark matter could continue converting into ordinary matter and there would be too little dark matter today. Somewhere between those two values is the right value, and there's some way you can quantify this to tell you how much, based on how much dark matter there is today, how efficiently this process should occur. Okay, well, how does that help us? Well, if this picture can happen, then just like Rhimes and Cohen, we can rotate the picture. Then that means this picture should happen. If dark matter can turn into ordinary matter, then it should be able to bounce off of ordinary matter. Dark matter should be able to fly through this room, come into you or an experiment, and kick something and leave some sort of signature. So that's your lamppost. That's how you can go look for it. So what do you want to do? You want to build a big detector that's going to allow dark matter to come in, smack something, and try and find that thing that's getting smacked. See that signature. So how big of a detector do you need? Well, dark matter is very, very weakly interacting. That is one thing we know about it. If it weren't weakly interacting, we would have seen it already. So it must be pretty weakly interacting, so you need a pretty big detector. The scale detectors that people are using nowadays range from a few tons, often of some liquid xenon, to smaller detectors that are the size of a few kilograms. But the point is that these are experimental sizes that you can do. You don't need a mountain to look for dark matter. But what you do is you go deep underground to shield yourself from cosmic rays, and then you try to eliminate background, because you don't want to see something and fool yourself and think you're seeing dark matter. Now, this process is a long one, and I don't want to belittle how difficult it is because it's incredibly difficult. This last step in particular is the quintessential one of all these experiments. But many, many projects are underway today to look for this precisely. The leading experiments in different areas are the experiment Xenon 1 ton, which is in a mine, well, it's in a lab under a mountain, not a mine, in Gran Sasso. LZ, which is in a mine in South Dakota. And Sensei, which is currently at Fermilab, which is actually a pretty small experiment. Just getting started. These two experiments are built based on the idea that you have a giant tank of liquid xenon, and dark matter will come in, smack a single xenon atom, which will then get a kick, make a tiny flash of light in the detector, and then you will detect that. And that's what they look for. It's an incredibly hard experiment. They have a ton of xenon in each of them, and they're going to get bigger. Sensei is slightly different. It looks for, instead of the nucleus of the atom getting smacked, it looks for the electrons getting smacked. So we take CCDs, which you used to have in your digital cameras, but you don't anymore, but it's a fairly standard technology, and they wait for dark matter to come in and kick an electron up into the conduction band, and then they try to read that out, just like you read out an image, but in this case it's dark matter. These experiments are very mature. There's ideas behind them that have been going on for over a decade in their natural progression. This experiment is very new and is actually still, it's pretty cutting edge in its approach. So, where are we in this search? People like to show plots that look like this, and I don't really care too much about the numbers, but let me just give you a sense of what is being shown. Dark matter could have a wide range of masses. So they put the mass of the dark matter down here. And dark matter could talk to us at a fairly wide range of scales. Even though we know the rate at which dark matter converts to ordinary matter, that doesn't exactly convert to how efficiently it scatters. It gives us an estimate, but not an exact number. So this is a measure of how much dark matter likes to smack into ordinary matter. This is the region which has been excluded by various experiments over decades. And this is where we are now. This is the region that's left, and once you get down here, neutrinos become a background for your experiment. So right now, all this is ruled out. This is the region which is still allowed. But who cares? It's just some plot, right? Is this interesting? Is this not interesting? And the answer to you is, it's interesting. I'll tell you what. At this point, you need to take a step back and say, well, how does the dark matter talk to us? This diagram, where dark matter converts into ordinary matter, I measure from looking at how much dark matter I see in the universe. But that's not a direct measure of how much dark matter will scatter off of ordinary matter. There's still a lot of variation in that, and it depends on what is this intermediate state. There's something out there that lets dark matter talk to us. The way we understand forces in quantum field theory is something akin to a basketball game. Okay? I take a basketball, I throw it to you, I recoil. Okay? You catch the basketball, you recoil. So there's a basketball. Right? The basketball, we're not directly touching each other, we're interacting with each other through something else. There's something else that's connecting us and allowing us to talk to each other and push off. And so too is how it should be for dark matter. So the question is, what's the basketball here? What's the thing they're throwing back and forth that's allowing them to scatter off each other? Well, one possibility is the Higgs boson. You've probably heard about the Higgs boson. It's the thing that gives mass to the fundamental particles of the standard model, not the proton, but electrons, quarks, gauge bosons. It's a very, very important particle. It happens to be neutral. It's something that dark matter can talk to. Okay? The dark matter can't talk to the photon because the dark matter is not electrically charged, but it can talk to the Higgs boson. And indeed, there are a lot of good reasons to think that it might. Right? Every fundamental particle in the standard model that has mass gets it from the Higgs boson. So it's a very reasonable thing to say, perhaps the dark matter also gets either all of its mass or a significant fraction of its mass from the Higgs boson. Higgs gives us mass, why could it not give the dark matter the mass? And if that's true, then that would allow us to talk to the dark matter by throwing Higgs bosons back and forth. And if that were true, then this is where you should end up on this plot right here. Okay. Down here in a region which is currently partially excluded and partially not excluded by the current experiments. So that's a very exciting thing, because that means that the experiments that are ongoing right now are answering a qualitative question. Does the dark matter get any of its mass from the Higgs boson? It's not just some number on a plot. It's a really general question that you can ask. But another idea that's got more attention in the last decade is the idea that maybe dark matter is not super simple. Maybe dark matter is actually part of a dark sector. We're made out of stuff where there's all sorts of different forces. There's strong forces, there's weak forces, there's all sorts of different types of quarks and leptons and neutrinos. There's a tremendous number there's a tremendous amount of richness in the stuff that makes up us. And so it's not a huge leap to say, well, perhaps there is a richness in the dark sector as well. Perhaps the dark sector has its own dark forces as well as dark matter and dark particles. And you can take that a step further and say, well, if it has those dark forces, maybe those dark forces are the things that are talking to us. Maybe we, rather than the dark matter having a very, very small coupling under things that we talk to, maybe we have a very, very small coupling under the things that it talks to. And the one that people study the most is the idea of a dark photon, which isn't exactly like an ordinary photon, but it's related. But it's a dark photon, a photon of the dark sector that the dark matter interacts with, of which we might have a very, very, very small charge. And if that were true, then the dark matter would interact via this dark photon and turn into, convert or scatter off of ordinary matter. And even though this sounds like a very, very general idea, if you go back to that idea where you calculate how much matter there is in the universe, you can determine what the properties of this dark photon should be. And the place where these sorts of particles live is up here. Those are in the region which is currently being probed by the Sensei experiment. So down here, these xenon experiments will help answer the question, does dark matter talk to the Higgs boson? And up here, they will answer the question, does dark matter talk to a dark photon to us? As an aside, if there is a dark photon, you don't just have to look for the dark matter, you can try and make the dark photon itself. And what's interesting about it is because these types of particles tend to be light, you don't need to go to the Large Hadron Collider to make them. You can go to relatively low energy experiments. So they're building experiments to look for them in Mainz in Europe, in Jefferson Lab in Virginia, and in Stanford in California. So there are a lot of experiments that are ongoing where you take very, very high intensity beams of electrons with hope that they will spit off one of these dark photons, and then you can look for the signatures. But these things are still in the early phase, and it'll probably take a decade before we're getting results from them. Now, I don't know if any of these experiments is going to find dark matter or not. Okay? I don't know if dark matter is living under any of these lampposts. But I do know that even if we don't find it, this era is going to be answering qualitatively significant questions for particle physics. It's going to be answering, does dark matter get its mass from the Higgs boson? And almost answering the question, was dark matter ever in a state where it was going back and forth with ordinary matter? Because if it was, we should be able to see the scattering process today. But maybe it's something else. Theorists are creative. There are lots of ideas that don't show up like this. Maybe it's not even an idea we thought of. Maybe it's something totally exotic that's very, very hard to see. So you can ask this question, what if it's not under a lamppost? What are we going to do? Is that it? Well, the answer, of course, is no. This is an image of the Milky Way galaxy. So you take, well, an image of the entire sky, you cut it down the middle, and you unfold it. You project it like this. So this is the full sky. We live in the northern hemisphere, so we don't get to see the bright galactic center. We just sort of get to see the outer parts. But this is what it would look like if you could see the whole thing. There's a lot of bright stuff in the middle. There's a lot of dust in the way. But looking at this, you might start seeing some interesting features, like this. Here, this. Here. That's the Large Magellanic Cloud, and that's the Small Magellanic Cloud. These are dwarf galaxies. They're small galaxies that are in orbit around the Milky Way. Their masses are about 100 times smaller than the Milky Way, but we think of them as sort of part of the broader structure of the Milky Way. And these are just the brightest ones you can see. There are many such dwarf galaxies that are even smaller that you can't see. So what we have observed in the universe is that galaxy clusters are made out of galaxies. Those galaxies then have their own subgalaxies. And the question is, are there things that are smaller that you can't see? Because if you had some big clump, there's a big clump of dark matter that's around this. If it were too small, as soon as you had your first burst of star formation, it blows out all the gas and star formation turns off. So we actually think that this is not what it would look like if you could see dark matter, because the dark matter would look like this. Our galaxy should be full of dark objects that are just clumps of dark matter that are floating through the Milky Way. And studying their properties, if we could study their properties, would give us information on what the dark matter is. It wouldn't be as direct as putting it under the lamppost and making it or studying it directly in a lab, but we'd be able to see its properties and then infer certain things about it. And it doesn't just have to be dark halos. We expect there to be black holes out there. We saw the black hole in the center of the galaxy. We know there are other black holes out there. How many of them are there? How much mass do they make up of Milky Way? Could they be a significant portion of the dark matter? Maybe there are even other exotic objects. If dark matter has a cooling process, like we have cooling processes, then dark matter could form into small compact objects that would look like very, very dense things. They wouldn't be a black hole, but they would have very strong gravity localized in a small spot. So if you could see the galaxy with dark matter, it would look more like this. It would be full of small structures of whose size, mass, and properties we still don't know. But there are things that you can look for. I'm going to tell you about one. I'm going to talk, well, I'll say it in a second. The one that I want to talk about is gravitational lensing. Gravitational lensing is something that's been used for decades now to look for dark matter. I want to talk about a new opportunity to look for dark matter with gravitational lensing that I find very exciting. I'm studying myself. So the idea of gravitational lensing was first pointed out by Einstein, who noted that if gravity is actually a bending of space and time, then all objects should have their paths distorted by gravity, not just matter. So light rays that are passing near a massive object should be deflected. So perhaps you have some bright source, some star out here. You have an observer looking out into the cosmos, and between the two of you have some dark lens. I don't know what that is. Maybe it's a black hole. Maybe it's just a clump of dark matter. Maybe it's a dark star, if the sector can cool and condense into something like that. And the light ray should have gone along this path here, but instead, what you see is a light ray that came along here and then was bent to you. So the location of the star is not where it really should be. It's offset somewhat. Well, if that's true, then you have the possibility of looking for gravitational lensing. Try and start this. So what this is a movie of a gravitational lens, some dark object, it doesn't matter what, moving across the field of view. You have some background field of stars and galaxies, and this object moves across here, and you can see it leads to these dramatic patterns of lensing of the objects that passes in front. But that's only if these dramatic features, which are called strong lensing, are only situations that happen if the dark matter passes right in front of the object you're looking at. You might not be so lucky. So let's take another step. Let's look at the same plot, but mask out the strong lensing. Look at the stars up above. What you see is as this dark lens is moving across here, all of these stars look like they're moving, right? They're very subtle movements, but all of these objects look like they're moving. And in this image, they're not. In this image, they would have been stationary. But as this dark lens moves across here, the objects that are behind it look like they have some apparent motion. So, this brings me to something which is very exciting for a lot of people right now. And in fact, next week is going to start a whole workshop for 3 weeks here at Aspen on people who directly study the data that comes out of this satellite. It's the Gaia satellite. It's a European Space Agency satellite. It had launched a few years ago, and it produced its first full data set in April of this year. It's going to be producing data for a few more years, and it's an incredible mission. It measures, there are 100 billion stars in the Milky Way. It measures about 1 billion stars in the Milky Way. And it measures them incredibly precisely. So just to give you a sense, it's not a beautiful image, maybe, but it's beautiful in a lot of ways. So here's that same image, but in Gaia data. Each point you see here is a star. You can see the large Magellanic Cloud, the small Magellanic Cloud. Let's zoom in. Zoom in on the large Magellanic Cloud. Here it is. Then you can pick a spot there. Zoom in on that spot. This is what it looks like. Each one of these is a star. The accuracy of this instrument is better than 1/100,000th of a degree. Okay? That's how accurately it can measure the location of a star. And if you can measure stars' location that accurately, there are a few things you can do. The first thing that you can do with some of them is you can measure what's called parallax, which is that if I measure the precise location of that star in, say, January, and then I measure the same star in June, then the angle, because the Earth has moved from one spot in the solar system to another, will be slightly different. And if you can measure the position, the angular position very precisely, you can measure that change, and that change tells you how far away it is, which is actually a very hard thing to do in astronomy. So by measuring the parallax of these stars, you don't just see where they are on the sky, you can see where they are, how far out they are. But for the discussion here, what's also critical is that you can measure their motions. Stars in the Milky Way are moving across the sky at amounts that are about, in this language, about 1 or a few milliarcseconds per year. An arcsecond, so a degree is split into 60 arcminutes. An arcminute is split into 60 arcseconds. And an arcsecond is split into 1,000 milliarcseconds. So that's how small this motion is. But the measurement accuracy of this experiment is 10 times better than that. So it can actually watch these stars that you look up at and look like they're fixed on the sky. It can actually watch as they move across the sky ever so slightly. It can measure incredibly tiny motions of these things. So why is that exciting for us? That's exciting for us because you can imagine you might have some background stars, and you might have a dark object that moves in front of you, like we described before. Doesn't lead to any profound, strong lensing warping signatures, but just leads to these very, very subtle induced motions of the objects. Now, stars are moving, so this is a complicated problem to solve. What you have to do is you have to look at many, many, many stars and ask, all together, do they add up to a net motion that looks like there's a lens moving in front of you? So a lens, if it moves, should produce a very specific pattern of motions. So in the middle, they point one way. Up here, they point out like that. On the sides, they point down, and it comes back in again. There's a very specific pattern of motions that a moving lens will induce. So what you do is you find all those stars, and you ask, if I add up all their motions together, do I get a consistent signal that looks something like this? It's a hard thing to do, but you have 1 billion stars. So you can look for these very, very faint signals. Now, I wish I could show you what the limits are, but their first data just came out in April, and this is something that my group is actively working on, especially my postdocs Ken Van Tilburg and students Anne-Marie Taki and Christine Mondino. But by winter, we will know. We'll start seeing things, or not seeing things. But by winter, we'll start having very, very interesting results. But the point is, this satellite, by looking up and measuring things incredibly precisely, gives us, this is just one example of a new window into looking at any type of dark object that's out there and understanding its properties. And this is what I refer to as the elephant scenario. The idea of the elephant scenario, I should have actually stepped back and I should have told you the reason why people talk about lampposts. The reason people talk about lampposts is because there's this old joke about a drunk who looks for their car keys, and their friend comes out and they're looking over here under some lamppost for their keys, and they're like, I can't find the keys. They're like, where did you lose them? The drunk says, I left them over there. He says, why are you looking here? He says, well, this is where the light is. This is how dark matter works, right? You look where the light is. You try to come up with as many lampposts as you can, but that's the only place you can look. So you try to be creative, develop as many as you can. But it may not be under a lamppost. And then we might find ourselves in a situation, the story of the blind man and the elephant, right? Where you reach out, there's something there, you reach out and you feel it. You can't feel the whole thing, you just feel a part of it. And maybe together you feel enough of it to get some idea of what it is, but you're never really going to completely see it. So even if we never get it under a lamppost, we have the possibility of feeling the elephant of dark matter that's out there, because it's there. It's all around us. It's feeling the Milky Way. Its properties should imprint on the signals that we can see in Gaia and future stages. So, I don't know what the future is going to be. Maybe it's going to be a lamppost. We'll come up with some clever lamppost. It'll show us some part of it. That'll give us an idea what we should look for. We'll build more lampposts, and all together we'll get a complete picture. That's dark matter. Maybe. Maybe not. Maybe we'll reach out, and we'll find some tiny part of the dark matter, another part, and then the rest we'll just have to fill in from our imagination. I don't know which one it's going to be. But there's a lot of stuff going on, both in a lamppost and an elephant. So, let me conclude. We live in a very exciting time for dark matter research. It's incredibly exciting. We are answering, from the particle physicist point of view, very important qualitative questions about dark matter. We're answering the question, does dark matter talk to the Higgs boson? The Higgs boson gives mass to every fundamental particle in the Standard Model that has mass. Does it give any mass to dark matter? We're going to answer that question. In this era, if there is a dark sector with a dark force that has even a tiny connection to us, we have a great chance of finding it. That's going to take a while, but we've thought about it, there are experiments lined up, and that's a research mission that will go forward. And in this era, using Gaia, we're going to start getting information about whether there are black holes, how many, how big, compact objects, dark halos that are moving across the sky and leaving an imprint. People tend to be impatient. People want everything to be discovered right now. Right? Certainly, especially when I was younger, I wanted everything to be discovered right now. Right? But discovering the neutrino took 20 years. That was a particle that you knew where it came from. Discovering the Higgs boson after it was hypothesized took 50 years and billions of dollars. Finding dark matter, well, we're already almost a century into it, but it's something where we really know even less about it. So it's not surprising if it takes us a long time to really find what it is. But in that process, we're finding out things about what it's like. We're seeing these halos. We're learning about black holes. We're looking under lampposts. We're learning more and more. Even negative results give us tremendous insight into what happened in the early universe. And that's really important. So no matter what happens with any of these experiments, the future of dark matter research is incredibly bright. I'm sure we'll be looking for it for quite a long time to go. So thank you very much.
Thank you very much, Neal, for a wonderful talk. We do have some time for questions. Do you maybe want to take questions?
Does dark matter obey the same gravitational laws as regular matter? For example, will gravitational waves be affected same R-square inverse R-square dependence?
Yeah, so we believe dark matter should have the same gravitational interactions that ordinary matter does. So gravity, in Einstein's theory of gravity, gravity couples to any form of energy. Right? So as long as dark matter has energy and mass, then it should couple to gravity. There are some additional questions you can ask that people currently are asking, which is, the important thing about gravity, from a cosmological point of view, is it's the only really long-range force that exists. Right? Electromagnetism is a long-range force too, but things are electrically neutral on large scales. So there aren't electromagnetic pull between Earth and the sun, right? Except for some radiation pressure, but that's not the same kind of thing. So cosmologically, the thing that's important about gravity is that it is a force that can extend all the way across the universe and influence anything at all scales. So we believe that dark matter should feel that gravity. And so then the question, probably the first question that one wants to ask is there anything else that dark matter has? Does dark matter have any other long-range forces that can stretch over incredible distance scales? And that's a question, that's an open question for a lot of research. When we study the properties of dark matter on the scales that we can, it doesn't look like we see any need for that kind of a new force in general. There are some constraints. In particular, there's something called the equivalence principle, which is Einstein said that a freely falling body doesn't know that it's in a gravitational field. You can't distinguish a freely falling body from a gravitational field. Another way of saying this is that all objects feel gravitational pull the same way, right? You drop a brick, you drop a golf ball, they both fall the same, neglecting friction. If there's a new long-distance force that only dark matter feels, then that would not be true anymore. And that would be important because you have these dwarf galaxies like the Large Magellanic Cloud that are orbiting around the Milky Way. And if they felt a different force from the matter that's inside of them, because they've got all this luminous matter that's inside of them, right now they're all moving around together because they feel the same gravitational force. But if there was a different force that the dark matter was feeling, then it would start leading or lagging the ordinary matter, depending on the sign of the force. And you would start ripping apart that galaxy, that small galaxy. Okay, so it would get pulled out from behind because the dark matter would kind of get ahead of the ordinary matter, and then it would kind of like trail out behind it. So you'd be tearing apart these dark galaxies. So there are limits like that on how strong the dark matter force can be. So it looks like probably the force, if there is a force like that, it should be weaker than gravity, at least on galactic scales. Now, there's some interesting work that's being done by Justin Corey and collaborators at the University of Pennsylvania, which is very speculative, but is also very interesting, where dark matter is not a single phase system. And so we know that ordinary matter can exist in a variety of phases, right? You take helium, you can have it be gas, you can turn it to a liquid, and when it's a liquid in particular, it's a superfluid. Cool enough. And his idea is that perhaps dark matter can exist in multiple phases. And the thing is that when you go into some of these additional phases, new excitation modes appear, which can be massless. Why do you care? Effectively, what that means is that there's some way you can kick the system, like in a superfluid. There's some excitation of the system that doesn't carry any mass. Okay? Producing a neutrino costs you a little bit of mass. Producing an electron costs you some mass. Producing a big photon costs you a little mass. Producing a photon doesn't cost you any mass. So a photon can be a long-range force. So if in this new phase there are new emergent modes that are massless, there could be new long-range forces. Long story short, his idea is if there's some superfluid phase of dark matter, maybe inside that superfluid zone, there are new long-distance forces that could appear. But then when you got to too dilute of a system, then those long-distance forces would go away. This then complicates these types of analyses I'm talking about, because some places have new forces and some don't. Anyway, this is a long, long answer to your question. Right now, all the evidence points to the idea that dark matter's interactions look like ordinary gravity. We don't see any evidence that we need a new force for dark matter. But until you know what it is, until you start seeing these properties, you wouldn't want to rule out the possibility. Stick to what the data tells us. Other questions?
Why is dark matter globular when our matter tends to be this way?
That's a very, very, very good question. So you start with some inhomogeneity. Okay, so you've got some overdensity. The universe is roughly uniform, but there's some place where you've got a little bit more stuff. Okay, some big ball. That then gravitationally starts to pull itself in. Okay. Now, what can stop something from just collapsing on itself? There's two types of motions that can stop things from collapsing on themselves. One is sort of random motion, like if you have a balloon, the molecules inside the balloon are moving in random directions. Okay, so they're not going to collapse the center because they're sort of a random motion. And so that's what we believe happens with dark matter. There's dark matter just moving in random motions. Ordinary matter doesn't collapse because it's moving in a circular motion. That's the other thing that can keep it from collapsing. So the real question is, as you say, why are they different? And what we believe is that with ordinary matter, you have cooling processes. Okay? Ordinary matter has interactions with photons. You form molecular hydrogen. Those things can then emit radiation. That allows you to take a hot gas, where things are moving randomly, and cool it down. When that cools down, what happens is it tends to collapse. And it collapses into a direction where there's some rotation. So if you imagine this big ball had some tiny, tiny, tiny bit of motion to it, right, initially. And when it collapses, you get the phenomenon that you observe with ice skaters, right? Where they've got their arms out, they can move moving, they pull it in, and they speed up, right? So that's what happens with the ordinary matter. As it starts falling in and cooling off, it starts speeding up and spinning more rapidly, and then you have an instability where everything collapses into a pancake and cools down. Because it no longer can support itself by random motion, so it supports itself by a circular motion where it doesn't lose as much energy. But we believe that the dark matter probably has some little bit of angular momentum too. It's spinning a little bit. But since it doesn't have a cooling process, it can't spin up. And if it did have a cooling process, it would spin up. People talk about this idea that perhaps there's some component of the dark matter that has collapsed into a disk through some cooling process. We don't see any evidence for it. There are limits on it. And that's one of the things people are looking for. One thing I should have said, by the way, is, I had on a slide, is that the next week, the speaker will be Mariangela Santi, who is here here for the Gaia workshop, who will be talking entirely about what you can do with Gaia. I talked about one thing, she's going to be talking about a whole host of things that you can do with Gaia. One of the things that people have done is look for a dark disk, whether some component of dark disk exists. They haven't found it using the Gaia data.
Yeah. I just wondered, could in principle the the dark matter interfere with gravitational wave from collapsing black holes or neutron stars, for example?
It's pretty dilute, so it shouldn't give any sort of significant viscous drag to the gravitational wave. So I haven't thought about it, but the reaction is the total energy density is so small that it's not going to do anything. There's no way to dissipate that energy through the motions of the dark matter.
It seems kind of remarkable to me that so much of the universe could be made up of something that we're having so much trouble measuring. And it makes me wonder, there's a heroic assumption that seems to be going on that the basic laws of physics apply to dark matter. Is there any research that is approaching this, assuming that the basic laws of physics that we think about aren't actually applicable?
There is. There's something called modified Newtonian dynamics, or MON, which is the idea that you give up on Newtonian gravity, which is what tells you that these rotations should be a flat rotation. And instead you say, well, there's some modification to the laws of gravity that explains that. My personal attitude about it is that until we find dark matter, somebody should be working on understanding that idea. But that person needs to be very smart. It's a very hard thing to do. This is not an easy thing to do, to actually come up with a consistent theory like this. You should be intellectually honest, because there are a lot of problems that you run into when you try to do this. And they should have tenure. They're not going to get tenure working on this. So Justin Corey of Pennsylvania, his idea is something like this. So it is something that one should think about, but there are reasons why it's very, very hard to do this. There's an understanding we have that when you go from short distances to longer distances, that you can understand what happens. Okay, so for instance, if I understand, in principle, if I understand the basic electromagnetic laws of protons and electrons, and then I build them into a molecule, I can derive the elastic properties of the rubber that's built out of it. I mean, I can, but in principle, I could. And the idea is that the large-scale effects that you see are derivable from the small-scale things that are going on. And so if we think that we have tested and understood gravity on relatively short-distance scales, it's very hard, but not impossible, but it's very hard to have a consistent theory where some new thing starts turning on at very long distances, which is kind of what you need. Right? We've studied the properties of gravity incredibly precisely here. For instance, there are mirrors that are left on the moon where we fire lasers and we watch as we both fall in our orbit around the sun, because that's what we're doing. We free fall around the sun. And we see that gravitation, that Einstein's theory of gravity works better than like a part in 10 to the 13th. So we've measured it in experiments like that. We measured it in experiments where you look at very, very short distances here on Earth, where you bring things close together and measure gravitational force. We don't see any effects there. The point is that everywhere we believe we understand how gravity should work, it works. And the next thing is, if I just assume, and we know that there are particles like neutrinos that you can't see, so it's not crazy to say that there's things you can't see. If you make this one assumption that there is stuff out there that feels gravity, and you put it into your cosmology, you can explain all the things that I saw, right? I can understand the abundances of light elements. I can understand the properties to incredible precision of the fluctuations in the cosmic microwave background. I can understand the fluctuations that have formed in the galaxies and galaxy clusters. But I can also do something like look at a galaxy, measure the motions of objects in it, and then look at light bending around it and see if those give me the same answer, and they do. And for instance, in the bullet cluster, you actually have a dramatic instance where the visible matter has separated from the matter that's causing the lensing, right? So most of the matter is here, the visible matter is here. So if it were simply a modification to the laws of physics, then, if it were simply a modification to the laws of gravity, then that should still be at the center of the gravity. Now, you can come up with a theory where there's a lag when you pull something out and the gravitational force lags behind it, and you can do that. But that's not the simple assumption. The simplest assumption is there's some stuff we can't see, we don't know what it is, we don't know where it came from, we don't know how it acts, but it couples to us gravitationally, and we can see its imprint again and again and again and again. And right now, that explains everything that we see in every situation that we believe we can calculate. There are some situations where we're not as good at calculating, where we're not sure it agrees, but we're not as good at calculating those things. Those are points of serious contention. But because it's so hard to come up with a modified gravity theory, and because dark matter does such a good job of it, the conservative assumption right now is there's stuff we can't see. That's the conservative thing to it. It doesn't mean that it's right, and you should find it. Right? You should see its imprints, maybe more with these gravitational waves, these gravitational signatures or something like that. But it doesn't mean that it's right. So that's what I'm saying. Until we find it, somebody should be working on it, but I think that that's probably not going to end up being the right answer. Yeah.
When we discovered the Higgs boson, we thought it would prove dark matter. What properties does the Higgs boson not have that doesn't prove dark matter?
So why is the Higgs boson not dark matter?
Yeah.
Because it's unstable. If you make a Higgs boson, it decays almost instantly. So when you actually look for Higgs boson, what you do at the Large Hadron Collider is you make it, it exists for a fleeting moment, and then it decays, usually into, usually into two things. Those two things can be a variety of things. But for instance, it often decays at one time in 1,000 into 2 photons. So what they actually did, the first way they found it, the most clear way they first found it, was when it decayed into 2 photons. You take those 2 photons, so you go to your experiment, you look at all the photons, you find situations where you have pairs of photons, you add up their energy, and you make a plot of all that, and you see if there's a bump. That bump is the mass of the Higgs boson, the combined energy of those 2 photons. And seeing that very clear bump was the first sign of Higgs boson. But the Higgs boson itself is not stable. Now, there's something else to the Higgs boson, to the story of the Higgs boson, which is the vacuum expectation of the Higgs boson, or VEV, as part of it is like called the vacuum expectation value. It takes too long to say it. You say it a lot. And what it is that in this room, more or less, there's no electromagnetic field turned on. There are weak electromagnetic fields, but more or less, if you want to turn on an electric field, that costs you energy. Okay? So electric fields like to be at 0. Magnetic fields like to be at 0 because it costs energy to turn them on. But that's not always true. For instance, if you're inside a ferromagnet, if you happen to live in a universe where you, instead of having empty space, you live with a bunch of iron atoms floating around you, and they were hot. They each have dipoles, okay, and those dipoles are magnetic moments. They're little magnets, right? These little atoms. And if you cooled your system down, what would happen is the system would cool down into a system where those magnets like to line up. It's energetically favorable for them to line up. So for a person living in that universe that's full of these iron atoms, when the universe cools down and these things freeze into their pattern, if you do it slowly enough, you will live in a universe where there's actually a magnetic field turned on. So that's a universe where it's actually energetically favorable to have the magnetic field turned on. Now, coming back to the Higgs boson, we don't understand why, but the way we write it down, the Higgs boson is actually energetically favorable to turn on. So in the early universe, the Higgs boson is off. Then when the universe cools down, the Higgs boson turns on. So everywhere in the universe is full of Higgs field, and that background Higgs field is what's actually giving the electron mass, the quark's mass, and things like that. But the energy that's associated with that turning on doesn't look like dark matter, because there's some difference from 0, possibly, between that and 0. That's just a uniform energy throughout space. So that's a contribution to the cosmological constant. The only thing is that if you calculate how big the contribution to the cosmological constant is, it's like 60 orders of magnitude too big. So, but that's a separate problem. But energy of space doesn't coalesce. If space itself has energy, that doesn't coalesce into a galaxy, right? In a galaxy, it's a place where there's a lot of stuff that's coalesced. So Higgs boson falls apart, decays, it's not stable. Dark matter needs to be stable. The Higgs field it's on doesn't coalesce, so the energy, whatever energy is associated with that, doesn't clump into stuff, so it can't be dark matter. So, but it's very, very possible that something talking to the Higgs boson, we have a lot of theoretical reasons that I didn't go into. We don't understand why the Higgs boson mass is what it is. We think that there might be other particles out there that are sort of controlling the mass of the Higgs boson, and it's very possible that those particles could be dark matter. So we hope that we'll make something related to them at the Large Hadron Collider, but